All right, I start the record again for the new session. Brayden, I think you're next. Um, oh, Brayden, I think I cannot hear you. Um, is anyone
Whoops.
here?
Is that better?
Yeah, that's better now.
Okay, perfect. Thank you.
No worries.
Perfect. Hey everybody, my project focuses on the autonomous detection of frame time anomalies within graphical processing data. Here is a quick look at our agenda, pretty much just the same as what Danielle showed. Player opinions regarding specific video games have historically been affected by outliers in system performance. This isn't necessarily new. What is new is applying an autonomous solution to identifying those outliers in live practice. In doing so, we can directly map out the exact moments within a gameplay session that overlap with frame time anomalies. Understanding the past studies on frame rate related negativity towards player enjoyment is integral to understanding the flaws in video game design. My goal is to provide a path forward for game designers to be able to effectively pinpoint the abnormal areas within raw frame rate data. They can utilize this with their understandings of their engine work to make improvements for their future works to prevent instabilities from popping up further. Evaluating both the history of time series anomaly detection directly with the reports of sentiment analysis, we can apply them in new opportunities that provide clarity to the nuance required for making the most of the quantifiable data we can collect with time series anomaly detection. Time series anomaly detection has an impressive history of adaptive use. Industries of all kinds use it for identifying irregularities in data. Expansive research has been done on this as a topic and provided a lot of the background I'll be using. Long short-term memory autoencoding stands as an important step in predictive detection by utilizing temporal data in deep learning to recognize changes in time series data while recognizing pattern changes down the line. Without the qualitative understanding, the quantitative metrics aren't going to mean anything. As such, most of my initial inspiration comes from my understanding of the frame time consistency on player engagement. This is what drove me to finding a way to identify these frame time anomalies autonomously for an easy way to identify where inconsistencies happen, without any processing from video data causing errors in the data output. Time series anomaly detection provides a strong avenue of identifying these points of failures within a game's raw frame rate data. Collecting and pre-processing that raw frame rate data is the first step, followed by implementing it into a data sequencer designed for proper input formatting in PyTorch machine learning. Long short-term memory autoencoding can then be used to record the instances of frame time inconsistencies. An autonomous approach seemed the most effective to me as it reduces the friction of processing the data by hand to outline any abnormalities. When calibrating a long short-term memory autoencoder, it takes quite a bit of math to get it going. I would know after having struggled to get it to accept anything for input for several weeks. I decided to use Python, being my most comfortable development language. Conveniently, it has just the right tools I needed in modules like PyTorch for the machine learning implementations, along with pandas and NumPy for the adjustments to the data shape for the autoencoder to recognize the inputs properly. Adjusting the data input properly into sequences for the autoencoder to look back upon for its learning stages was integral to making the program operate. Imagine trying to teach a foreign language to somebody who only speaks their native tongue. Completely foreign concepts might have some convenient overlaps that we're unaware of before learning it. But in the case with machine learning, we need to translate those overall ideas very clearly without any room for nuance. In this case, we're giving the machine the translated data that can then be properly utilized in the equations it can use to repeat and learn the patterns within our data. In my case, FrameView CSV files were included to record the overall frame rate data of one play session, and then the system can actually detect all of the anomalies over time as we feed it through. Running the learning segment teaches our model to identify with a high degree of accuracy which points within the FrameView data are abnormal. This was originally the part I was most worried about, but ended up being fairly easy to achieve overall. The data sequencing was far more difficult, as I needed to find exactly the right shape for the data input to properly be recognized. Otherwise, the entire model would break down. The data collected during my project was obtained utilizing that tool I mentioned earlier by NVIDIA. It's called FrameView. FrameView captures data on every single frame that is recorded during a time frame of the user's choosing. So when you're playing a video game on your computer, a rough average of 16.67 milliseconds is the approximation for the average of 60 frames per second. Testing this data over time illustrates the real points of impact that happen within the recorded data, as we can see the exact measure of the milliseconds between each individual frame recorded. In my testing, I took separate variable time frames in minutes worth of frames and ran the autoencoder through some sequences of that data to teach it how to recognize faults in the data. I took a simplistic approach and decided to keep the scope narrow, just for testing the overall design before pushing forward, but still found incredibly effective results even in this small form. Right here on the graph, the anomalies are pointed out where the model is trained against. You can see it's actually fairly accurate. It only identified those 3 major areas where any frame issues occurred. It managed to catch the very lowest mark, but not always the very highest, but it always caught it within that little section there. Autonomously recording the anomalies within FrameView's CSV report was a novel contribution towards identifying graphical processing errors that can lead to further advances in the field by analyzing the system diagnostics correlated within those very same frame times to identify what problems might be happening underneath. Even in such a small segment of the overall data I collected, I was able to, within just a few minutes of running the program, identify those exact sequences of time where the game had performance issues. My intention was identifying how FrameView data could be utilized in a long short-term memory autoencoder approach to effectively showcase how automated time series anomaly detection could be used to better identify errors within the video game engine design to improve their overall efficacy. Time got the better of me, and I had to settle for just getting something functional ready and prepared. What I found was my expected goal reached. I'd created an autoencoder capable of identifying those anomalies with a very high accuracy. The slideshow here on top showcases how my results were reflective on multiple sections of recorded frames from my Elden Ring recording. On the bottom, it shows some areas where my expectations were not met. One can be seen there at the very end. I actually took a different game series for this one. I showcased some Overwatch data, and I did discover that FrameView's CSV report won't know how to differentiate between different frame rate locks. And so that's something that I'll have to tune out a bit better in future work, but it threw everything off overall. Analyzing the past examples of time series anomaly detection within different industries provided me a starting point to explore more depth within this novel idea of iterating anomaly detection within a different angle of the video game industry. FrameView aided a lot of my data recording by providing direct graphical frame rate data to be utilized. As a result, the flaws that can occur within that data can be detrimental to my program's success, though. I'll need to keep this in mind when improving the overall design and attempting new data inputs. My project created an opportunity for me to stretch my comfort zone well beyond what it was before. I successfully created a long short-term memory autoencoder that identifies anomalies within FrameView data, and with future efforts applied, I can iron out the quirks and expand upon the studies of past research in quality of experience for player sentiment. I'm incredibly excited to see what new contributions can be made with this. Here is my demo. Got no audio with it, so I'll just kind of walk through it as I go. I used a simple Jupyter notebook just to keep everything concise and narrow. But pre-processing all the data and shaping it properly was done in that first step. Next was actually loading the model properly beforehand and making sure that the batch sizes were correct so that it didn't run into any issues during the training. And then the training takes the longest. It actually has to run iteratively over every single sequence multiple times. It shows which batch or which epoch we're on, as well as the loss for each one. That varies a little bit over time, but it's extremely accurate, being in like less than a percentage of difference. Whoops. There we go. And then afterwards, I am loading out all of the data that I need from the model itself, and then mapping it out on a graph. It's not as crazy fun as Danielle's is, unfortunately. Here are some of my key references. Just for the sake of time, I'm going to go ahead and leave the talking section I had here behind. So I will go ahead and open up for questions.
Brayden, did you, with like trying to do an analysis on frame rates in video games, is you compare it to other hardware? And the one thing I didn't see, I don't know if I missed it or looked away, is did you declare like the specs that you're using to record this?
No, that's a great point. I did not. The actual data it uses from FrameView uses your native your native computer parts.
Mhm.
So it'll actually just tell you in your output as well, like what you're using in the FrameView sheet.
Right.
So whenever like say if I shared this program with you, you could record it all with your own like data. And it'll tell you which parts you're using and like how they're comparing. In future work, that'd be a really good idea to have it just compare with past examples and benchmarks that other people have used.
Yeah, I mean, because obviously with NVIDIA, especially if you're using uh, one of their graphics cards, is like it can be. I mean, we're seeing data comparison on frame rates, whether it's the 4900 versus the 5900.
Yeah.
Or yeah, 5090, 4090 versus the 5090. And I mean the 4090 is being compared to the 5080, so as having similar rates, and that's where like knowing what the hardware is that you're testing it is, are
Yeah.
those same anomalies happening on the more advanced, more expensive hardware?
Yeah. No, that's a great point.
So
With the scope of the course, I hadn't the opportunity to actually like test it on other systems. I could only do it on mine, but
yeah,
that wasn't something I thought of.
yeah, I mean it looks good on where you're going. It's just like I said, is that would be like just understanding the specifications of the hardware that you're using, so that especially with, I mean, when you get to AAA games, is like we need more RAM, we need bigger and better graphics cards.
Exactly.
And do you really? I mean, that's really what it comes down to, is that your tool actually could justify on the opposite of like, yeah, you really don't need to spend $2,500 on a graphics card.
Yeah. Thank you so much. Yeah.
So yeah, but great job.
Thank you, guys.
Good job, Brayden.
Thank you. Any other questions?
Doesn't sound like it.
Nope. Awesome. Take it away, Sean.